Okay, so let's talk about continuous conditional probability. Now really in spirit there's very little difference between this and discrete conditional probability. As you know about calculus, continuous is thought of as a limit of discrete. When you have discrete probability, each point in your sample space has a non-zero probability, right? If I draw my sample space here, then with a discrete sample space, you have points that have probabilities. Now, what happens with continuous simply is that the number of points goes to infinity, and the probability on each point goes to 0. So I can just say that. But a lot of the ideas go through. The other thing that you may know is that a sum turns into an integral. And in fact, the probability of x, the probability of some point, say, let's just call it a. Instead, because the probabilities of points is going to 0, this becomes more like something like p of x dx, right? Where you think of a small region in your sample space as having some probability proportional to the size of the increment that you use here. All right, so we'll be talking more about that. All right, so instead of having a conditional probability, we have a conditional density. Now, remember, you should think of this f of x dx as a probability. So conditional density, I'm just taking off the dx here, and I'm dividing by p of e. Now, this is analogous to the equation p of x given e is equal to p of x and e divided by p of e. We have p of x and e here because the conditional density is non-zero only if x is in e, and it's 0 if x is not in e. All right, so as I said before, when you use probability densities, you use an integral instead of a sum, and you include this dx to include the fact that each sample point has probability 0, and you think of small sample intervals as having probability f times dx. Now, naturally, we can talk about the conditional probability of an event f given e. In that case, we integrate over f. Now, you can, if you plug in this formula, then you're just using f of x, and you're integrating over E intersect f. So if you take out this 1 over p of e, which is a constant, you're integrating the density over the intersection of e and f. So there's this kind of symmetry between f and e. Probability f given e and probability e given f both depend on this probability of this intersection, but one is divided by e and the other is divided by f. Now he points out here that if you have a uniform density, then basically that means equal probability weight throughout the sample space. So all events of equal size are equally likely. And this will also be true for the conditional density. If you think, for example, of a probability of a uniform within a region, but then I know it's in the left half of the region, it's still going to be uniform in the left half of that region. So many probability problems have to do with uniform densities, and uniform density is just an area problem. And we've seen that already in our previous continuous probability section, where we integrated over squares and so on. All right, so here's an example. Okay, in the spinner experiment, suppose we know the spinner has stopped with head in the upper half circle, where x is between 0 and 1/2. What is the probability that x is between 1/6 and 1/3? Now, example 2.1 is back here. You have a spinner which consists of a circle of unit circumference. So notice it doesn't say unit radius, it says unit circumference. If it's unit circumference, then I can label the points around the circumference from 0 to 1 according to the length. Now don't be confused, usually you label a circle from 0 to 2 pi, but he's saying that this circle has total length 1 and not 2 pi. Right? So we're looking at the event from 0 to 1/2, so that would be from 0 over to here, from 0 to 1/2. And as it discusses in the chapter, this x takes a uniform distribution on the entire circle. Right? But if I know that I'm in the upper half plane, then that's restricting me to the upper half of the circle. Still uniform on that upper half, but it's more restricted. So if we return to the problem at hand, we have in mind that x is between 0 and 1/2. What's the probability that x is between 1/6 and 1/3? Now, frankly, it really doesn't matter if you're choosing x with a spinor or if you're choosing x on an interval from 0 to 1/2. If you're choosing x on an interval from 0 to 1/2, then what you want to do is take the ratio of the length of this interval to the length 1/2. And that length 1/2 is just exactly the denominator that exists in the definition of conditional probability. All right? So it works out to what we would expect previously when we took ratios of areas to find probabilities. We're getting this very, very same result. So in fact, if you know that the spinor is in the first half, or in the first half interval of length 1/2, you can work out that the density should be 2, because the total weight, total mass of probability should be 1. Right? If x goes from 0 to 1/2, then you have to have a height of 2 in order to get a total density of 1. And that 2 reflects the 1/2 in the denominator, because P of E is 1/2. Right? The 1/2 in the denominator becomes a 2 in the numerator. So that's where that comes from. So as I said, conditional probability is consistent with our previous ideas of continuous probabilities. Okay. Now in the dart game, you can do something similar. Now dart, you think about you have concentric circles. In this case, you want the probability that the distance from the center is less than 1/2. Right. Now this corresponds to a set. You know the distance formula. The set of points in the plane that are less than 1/2 from the origin, a distance less than 1/2 from the origin, satisfy this equation here. So that's the size of f. But we have to divide by the size of the target. Right, now I have to be careful when I read the problem here, because I missed something here. In the dart game, suppose we know that the dart lands in the upper half of the target. What is the probability that its distance from the center is less than 1/2? So we're restricting the area of the target to the upper half, and then also the dart will have to land in the upper half of the bullseye. Right? So this here is the area of the upper half of the bullseye, and then this here is, or actually this is the probability of the upper half of the bullseye, and this is the probability of the upper half of the target, right? Because the target has radius 1, so the area of the entire target is pi. So the area of the upper half of the target is pi over 2. So the probability of the upper half of the target is 1/2. Right? So, and you can see that the area of the upper half of the bullseye is given by this formula here. Right? Now, in this case, the conditional density function is the original density function, which was 1 over pi, multiplied by 2, which reflects the P of E, which is 1/2 in the denominator. So that's why you get this 2 over pi. All right, this problem talks about exponential density. We suppose we are observing a lump of plutonium-239. Our experiment consists of waiting for an emission, then starting a clock, and recording the length of time x that passes until the next emission. So you get a Geiger counter tick, and you start the clock, and then you wait until the next one. Experience has shown that x has an exponential density with some parameter lambda, and there's some theoretical reasons for that, which depends on the size of the lump. Suppose that when we perform this experiment, we notice that the clock reads r seconds and is still running. What's the probability that there's no emission in a further s seconds? Okay, so there's been an emission, you waited r seconds, nothing has happened, and then you want to say, well, what's the probability that there's no emission in the next s seconds? You waited r already. What's the probability that there's going to be an emission within the next s? Is that emission becoming more likely or less likely, or what's happening? So let g of t be the probability that the next particle is emitted after time t. All right, so here we're saying after, not within time t, after time t. Okay, then g of t is equal to the integral from t to infinity of the density function of the exponential distribution. Why t to infinity? Because this corresponds to the time greater than t. Right, so the particle is emitted after time t. And you can do this integral. And then here you have the event, the next particle is emitted after time r. You can see that that's a similar thing, except you're going to have a r here instead of a t. And then f is the interval, the event, the next particle is emitted after time r plus s. That's going to have the very same form, except t is replaced with r plus s. Okay. Now notice that the event f is the event that the next particle is emitted after time r plus s. F intersect E is just the same as f, because if the emission is after time r plus s, then it's certainly after time r. So f intersect E is the same as f. Right? So that comes into play here. The probability of f intersect E is going to be this g of r plus s. As I mentioned, to do this one, all you have to do is replace the t with r plus s. And then in the denominator you have e. E is waiting until time r, so I'm going to replace the t with r. If I take this ratio and work it out, I get e to the minus lambda s. Okay. Now the significant thing here is that this probability is independent of r. It doesn't matter how long I've already waited, the time until the next emission still has the same probability distribution. And this is called the memoryless property. We've alluded to this before.